So yeah, just so we're on the same page, here's roughly, what's it? Q4, Q5, Q6. Here's roughly what your exam will look like. So the first three questions have typically been about cement and all the cementitious material science stuff that you learned in the first 2 weeks. They're 3 questions, but they're not worth very many marks. So this only accounts for about 20% of the finals mark, whereas these last 3 account for about 80% of your marks, right? So yeah, I'll run through what these topics are, just so you get a full scope of what you need to study, as well as show you examples from past exams, which I have also in the folder. And then we can also decide which kind of questions you want me to run through today. Again, I mentioned I think everyone might be at different stages in this course. This course is structured a little weirdly. There's no midterm, right? So I know a lot of people, they do the assignments. They might even get resources from previous years, chuck the numbers in the Excel calculator. So literally some people haven't touched the course since week 3, week 4, whatever, right? That's fair enough. I'll do the same thing. But the finals is a real hurdle now because there's no midterm. So all of the stuff which is in the course is accessible. Is what I'm saying, right, for the finals. But yeah, let's run over the concepts. Oh, firstly, I'm not a great material science guy. So cement-related questions, I'm not going to be able to answer very well, but I think I can handle the solid mechanics related stuff in the last kind of those possible topics, which will be in questions 4 to 6, right? So there'll be flexure, shear, serviceability, and columns, right? So and every now and then you could also have a mix-up, one-way slabs, but one-way slabs are basically just going to be a version of flexure, shear, or serviceability, but framed in terms of one-way slabs. Okay. Yep. Does anyone have any questions so far about exam structure or anything like that? Nope. Okay. Basically, actually I might talk about this a bit more. So I think students, when they're doing this course, generally start losing the plot around flexure, right? Because flexure is a huge hurdle. It requires 5 or 6 different skills from solid mechanics, and it's very easy to get lost, right? Whereas the topic shear and serviceability is more about following steps, and you don't actually need to fully understand the topic in order to do those questions, if that makes sense. If you have a good set of notes, which if you scan the QR code, you can just have a copy of my notes if you need them. If you have a good set of notes, you can get through shear and serviceability fine. But flexure you genuinely need to know because every question is different and you need to derive every question kind of in its own way. Similarly, columns will use a lot of the techniques which you'll be using in flexure as well. So it's all about deriving based on a cross-section and learning a bunch of methods, I guess. It's kind of like in eng mechanics when you have to solve for a bending moment diagram for the first time, you know what I mean? There's no formula that you can follow to do it perfectly every single time. You're going to need to know the exact method and steps behind that. Yep. Okay, anyway. So let's talk about flexure and columns a little bit more deeply, right? There's a couple. I've narrowed it down to essentially 4 different methods you kind of need to know. These are the skills you can think about it like that. The fundamental skills you need in order to solve these questions. And this is where the hurdle comes in this course and where students start to lose the plot. Because this is all taught to you very quickly, right? So the first one is finding shear force diagrams, bending moment diagrams, right? That doesn't sound very bad, right? So that's finding your B star, M star, right? And I think most people can handle that. It's basically an extension of Eng 1300, the statics part of it. So usually for a simply supported beam, like this for example, the shear force will look like this, right? And then the bending moment diagram might look like this. If you're wondering where these little jumps are, rather than having like a perfect parabola. If you're wondering where the jumps are from, it's due to an assumption we make with the beam and column connections. It's called a rigidly connected, yeah, I guess just like a rigid beam to column joint, right? So it has a little bit of rigidity, so it has like this little jump. It's called a hogging moment in the bending moment diagram. But yeah, this would be like where your positive moments are, this is where your negative moments are, and etc. How's everyone with this stuff? You reckon? I just want to gauge if you feel comfortable with this kind of stuff. Another thing to note is, you might also see continuous beams, right? And we don't really necessarily learn how to solve continuous beams in 1300 because they're statically indeterminate. There's too many unknowns, right? So you can't solve it using the normal methods that we learn. But instead of using the methods that you learn in structural analysis, right, 2303, the standards, right, the concrete standards, have a little simplification method that's listed, and it's a lot faster to follow those kind of formulas than trying to use the methods you find in 2303. So essentially, your shear force diagrams might look like this with the shear force envelope in mind, right, for a continuous beam, right? And your bending moment diagrams might look something like that, right? And just finding those values that they're found in the simplified method in AS3600, right? If you've never seen this before or never heard about it, don't worry, I've got notes on it, and we can run through it as we go. But yeah, I'm just giving you like a general overview first. Another thing to keep in mind is, where do these stars come from? So this is called a factored load, right? So instead of directly taking the live and dead loads as the absolute load, right? Like in 1300, you would just say there's this amount of force on a beam or whatever, or on a truss, right? In this course and in steel structures, we essentially have these factored loads, right? So a distributed load will have the star icon next to it. And this just means we follow these load combinations, which are found in AS1170. Right, so these might look familiar as you've been doing the course, but it's basically saying that we take the worst case scenario, so we're going to exaggerate our loads. We're going to exaggerate our dead load by some amount, we're going to exaggerate our live load by some amount, and we'll take the worst case scenario out of those combinations, right? And then using that load, that's how we find M star and V star, right? Okay, so hopefully that one isn't too scary. The next one is using strain, like understanding the strain distribution. It's basically mapping out the strain in a beam versus the depth of the beam. And then using that information to check whether the steel is yielded or not. Right, so this is usually where students lose the plot. They're like, fuck is strain? But essentially, if you have a cross section, right, this is all from engineer's beam theory, which you learn in solid mechanics. But we use it a lot in this course, right? And you use it whenever a beam is bending. So if this is the cross section, we might see this epsilon, right, which is the strain. And then it will follow a curve. Sorry, not a curve. It will basically look like two triangles, okay? And yeah, like in the lectures and stuff, Taewon will derive this for a lot of different cases, such as like your uncracked section, your cracked section, and then in the case of flexural design, it's the ultimate moment, right? The ultimate case. That's where your beam is essentially like at the absolute point of failure, right? Yeah, so basically students like don't really understand the importance of this strain diagram, but I would say it's like the first step in understanding how to calculate the ultimate moments, right? And it's basically just saying that one side of your beam is in compression and one side of your beam is in tension, right? And for a simply supported beam, right? If you think of these fibers, right? The top fibers, as it's bending, are going to be compressed or pushed together, right? The bottom fibers are going to be pulled apart like this. And then that's where your cracks and stuff will form in concrete, right? So we just say that that bottom is in tension, and we say the top is in compression. So how do we express that? Well, we can express that through the strain diagram, right? This is a measurement of how much your beam is being pushed together or pulled apart, essentially, right? And what happens at this point here, you reckon? I'm going to start like trying to incorporate you guys into my discussion here. Like, does anyone have a like stab at what the strain is there? 0? Yeah. So that is the point of no strain, right? So if we put like concrete rebar at that exact point, is it going to be in tension or compression? Neither. So it's not being stretched, it's not being pushed together. When you have a point of 0 strain, it's literally not being strained in flexure. In flexure just means bending, right? So this is actually a really important point because this is what defines our neutral axis. That's the depth to the neutral axis, right? It's the point of no strain, right? And the depth of the neutral axis is always measured from the compression side, right? So if we had a beam that looked like this, right? And the bottom was compression, the depth to the neutral axis would be from the bottom side, right? Okay. So an important thing to note about the ultimate moment, right, or the point where the beam's like fucked, right, basically, is it's always defined by the same point, and it's based on the compressive strain. What defines the ultimate moment is when the strain on the outermost compressive fiber reaches 0.003. Say that right? 0.003. Yeah. Just keep that in mind. Like, you'll need this for almost every like flexural or column question, right? Just this information alone. So, is anyone familiar with similar triangles? That's my next point here. Yeah. So similar triangles is something that you can apply in like, algebra or graphing or whatever, as soon as you have a graph which is a straight line. So that's essentially what a strain graph is a straight line, right? And so we can apply similar triangles to check for steel yield. So just imagine, right? Actually, you don't really have to imagine. Here I've drawn the tensile bars, right? This point here, we can call it epsilon, which is a strain, right? You're straining your tensile steel. That's how we would denote it. If you had compressive steel as well, you can call it strain of compressive steel, right? So basically, you can calculate what these numbers are. You can always calculate what these numbers are for the strain in the compressive steel and the strain in the tensile steel. And it's because we know this number here, right? 0.003. And we know that this is the depth of the neutral axis, right? So we're saying that this triangle, so the rise of a run of this triangle, always has the same slope, right? It'll be different depending on where you, like how deep your neutral axis is, but it'll have the same slope for anywhere else you want to find on that triangle. So if I wanted to find the strain in the compressive bars, all I need to do is measure this rise, maybe we'll call it rise this way, this rise over this run, right, which you can calculate, you can back derive that using dn minus dsc, depth to the compressive steel, right? So these are the things you want to think about. The formula is really easy, it's just rise over run, right? It's similar triangles, but people usually get lost at where these algebraic expressions come from. It's literally just one triangle's slope is equal to another triangle's slope. That's it, right? So that's how you can find the strain in the So tensile steel. That's how you can find the strain in the compressive steel and strain in the tensile steel as well. Yep.
Instead of like using similar triangles, is like a certain formula that we can use? Use similar triangles?
Yeah, you can. But it depends what you're deriving. You know, it depends. Like sometimes you're trying to work out the tensile steel. Sometimes you're trying to work out the compressive steel. So you might mix up the formula in your head if you just try to memorize it. So it's better to just do this triangle is equal to this triangle. Yeah. But yeah, basically steel yield. Imagine, sorry, this is a bit of a stupid analogy, right? Imagine you have this bucket, right? It can hold a certain amount of water, right? And then once this bucket's full, can't hold any more water, right? And so basically your bucket is FSY. It's the limit of stress that your bars can essentially give, right? And then if the bucket's full, that's when it can't give any more stress, I guess, if that makes sense. So basically, while your bucket is not full, it's going to be expressed using sigma CS, right? And when it is full, FSY is usually 500 MPa, right? And you can find out how much water is in the bucket using the strain. Yeah, using strain, basically. And the elastic modulus. And you can backwork the stress. Make sense? Kind of? Okay, cool. Okay, next thing is stress to force conversion, okay? So I'm really running out of space, so I'm gonna start moving some shit. So deleting this. Okay, so stress to force conversion, right? Your stress distribution will look something like this, right? So that's your compressive concrete in the ultimate moment. That's your neutral axis. That's your tensile steel, right? So we're still modeling this cross section. And for its force, right, you have to basically turn that distributed load into an equivalent point load. Okay. And then you have to turn that stress into a force as well. So basically, force is equal to stress times area. So in order to get the force of the tensile bars, right, you have to get this stress multiplied by the area, for example. Same thing goes for the concrete. So we have this like distributed load, and then you multiply it by the area of concrete and compression, and that's how we get the force of the concrete, right? So again, these are very like simple equations, I guess you can say. Like it's literally one line, but there's nuance to all these steps, right? The other formula for converting the stress in, like, for example, the compressive steel involved finding the using the elastic modulus and then finding the strain of the compressive steel. And the strain of the compressive steel came from similar triangles. Do you know what I mean? So these are all like fraction equations, but like you add them all together, it starts to look confusing, right? You do enough practice though, and it all starts to come together. Okay. All right, and then lastly, we also have the force and moment equilibrium, and that's to find the depth to neutral axis and the ultimate moment specifically, right? So the ultimate moment is basically the moment couple of these forces. It's saying we take the sum of the moments about this neutral axis, and we consider all the forces and then the lever arm, right? You can do the lever arm however you want. You can do the lever arm as between these two things, or you can do it as this distance plus this distance, right? So whatever moments there are around that neutral axis, that's what our capacity is. That's the ultimate amount that it can take before the beam breaks, right? And that's what sits on this side of the equation. That's what we're trying to solve, right? However, to find that, we need to find the depth to neutral axis, right? So it's always, you always do it in this order. You always try to work out what dn is, you check the steel, and then you can find the ultimate moment, because you can't find the ultimate moment unless you know where the neutral axis is, because you don't know where to take the moment equilibrium around, right? Yeah, I feel like I'm starting to speak another language. Do you guys understand roughly? Okay, it'll make more sense as we go through examples, but this is just covering flexure, and like we apply these kind of methods to columns as well. Yeah, optionally we can also go through shear, we can go through serviceability, yes, just whatever, but basically I only have time for 2 questions, right? Because they're quite long and I want to go through them properly. So I'll tell you all the options. From the 2019 paper, there's designing the flexural steel and designing the shear steel and serviceability, right? Then they made it harder and they made it 3 questions instead of 2, right? Then question 4 was flexure, question 5 was shear, question 6 was columns, right? And this one involves shear envelopes as well. And then question 4 was flexure, question 5 was shear design in the context of one-way slabs, and question 6 was serviceability. I guess one thing to keep in mind is that flexural design and finding the ultimate moment is slightly different, right? So this was only 2 questions because these steps actually take quite a while. When you're designing a beam and you don't know how much steel is going to be in it, or you don't know what its dimensions are, that takes quite a while compared to just simply finding how much moment it can take based on constants, such as there's this much steel inside the beam, right? Okay. So yeah, basically these are options. Another thing to keep in mind is if you have any papers, if you get any papers from like StuDocs, for example, and they're from like 2017, even 2018, or any earlier, don't follow them religiously. And does anyone want to have a crack at why?
Did they change the standards at 2018?
Yeah, they changed the standards in June of 2018, right? So how you solve the questions is going to be different, slightly. It's going to give you different numbers for gamma and alpha 2, and other methods are slightly different as well. So they calibrated the standards in 2018, and they didn't update it properly until 2019. So all the 2019 stuff is up to date. Okay. All right. So basically, hopefully you've had a good chance to read this. I'm just going to do this based on a majority vote system. So chuck your hand up if you want to do a flexural question. Okay. Okay, chuck your hand down. Chuck your hand up if you want to do a shear question.
I'm going to do 1 question.
I'm doing 2. Alright, chuck your hand down. Chuck your hand up if you want to do a serviceability question. Okay, chuck your hand down. Chuck your hand up if you want to do a columns question. Okay, check your hand down. I'm pretty sure flexure 1. So we'll start with that, and then we'll revote for the second question later, right? Okay, so I'm actually gonna do. I think I'm gonna do this question because the design of flexure doesn't really teach you the principles of flexural design, because the design of like the flexural bars and stuff, you can actually not know any of those techniques I outlined above and follow a bunch of formulas and still get by, right? So I want to go through a flexure question that is like as core to the course as it gets, basically. All right. That's not it. So here's a question. Just give it a read. I'm going to pull up my own notes here. All right. So basically, we have a beam. It's simply supported. Question mark? Yes. It has your uniformly distributed loads on it, so it tells you what G and Q is over here. It also has point loads, right? They're both live loads here. It also tells you section AA is there, right? Yeah. So what else information is important? It also tells you this is the cross section, and in this type of question, the tensile steel is known, right? So basically, you won't need to design how much steel is going to be inside, right? You just need to use all those techniques I was outlining earlier to find, like the ultimate moment and stuff like that, right? So let's read through what's required in all the parts, right? So first things, bending moment, shear force, right? This is like 1300 revision almost, with the factored loads in mind. And then the next is finding the ultimate bending moment capacity, and then compare it to the bending moment diagram and check for ductility as well. If the section doesn't meet ductility, how much compressive steel do we need to add to ensure we have a ductility of this much, 0.3, right? Yeah, and then here's what it would be. Basically, there's a little note. Here's what it would look like when we add the compressive steel. So it tells you where to put the compressive steel in terms of the depth, right? All right, let's do this. Okay, so basically, for every topic, unless they give it to you, you have to find the factored loads first, okay? So you have to be really careful with the wording of the loading. Here it says they're unfactored, right? So when they're unfactored, it means you have to exaggerate the loads using the load combinations, right? If they give you the factored loads already, don't double up your factoring. Do you know what I mean? Okay, so basically we're going to find the factored distributed load first, right? Because these point loads, they're going to be accounted for separately, essentially, right? So we're just trying to find the factored uniformly distributed load which acts over the entire beam, right? This is basically the max of two numbers. One is 1.35 G and the other is 1.2 G and 1.5 Q, okay? So G is 15, right? And Q is 20. You can see that, right? Which gives 48 and 20.25 kilonewtons per meter, right? Okay, next we have to conduct basically 1300 statics. One more thing actually. Let's do PQ star. Basically, because these point loads are also unfactored, right? These are concentrated unfactored point loads of 18 kilonewtons. Because they're also unfactored, we should also consider the second case, right? Well, if you want to, I might do it like this. Basically, if the first loading case is going to govern, right, we don't have point loads because they're live loads, right?
Doesn't make a difference, but I think they're the values super.
I got the 48, 20.25.
Oh, did I?
Doesn't
Sorry.
make a difference. Though.
You're right, man. My bad. Let's fix that. Thank you. Okay. Basically, let's explain how these point loads work. If we have the case of dead load governing, right? So, for example, if it was actually 48 somehow, then we'd have to use these two combinations of loads together, right? meaning there wouldn't be any point loads for the case of purely dead loads. But for the case of dead and live loads, right, it's basically going to take into account both the uniformly distributed load and the point load. That's been exaggerated by this factor, right? Okay, I'm not going to calculate that because I didn't in my calcs here. Right. So let's redraw that beam. So this is a free body diagram, right? 2 meters, and then 5 meters, and then another 2 meters, right? And call this point AY, call this point EY. Alright, let's do it like this, right? So for the uniformly distributed load, it's 48 kilonewtons per meter, right? And these point loads were 27. Sorry, so let's do that again. 27, right? So we don't have any horizontal reactions because we don't have any horizontal external forces. So we can just look at the vertical reactions AY and EY, right? So again, this is the free body diagram. And what I like to do from here is I like to draw the shear force diagram underneath it, right? So we're going to use something I like to call the graphical method, right? Where I basically overlay this line horizontally down there, right? Okay. Oh, sorry. Let's calculate for the support reactions. So we take the sum of the moments, and if we take the sum of the moments at A, right, we're going to be solving for E. Yeah, because the lever arm, here are the lines of actions which extend infinitely in both directions of all of the forces, right? And when the lever arm is 0, so at this point the lever arm for AY is 0, then that's going to eliminate an unknown, right? So we're going to be solving for EY like that, for example, right? But if we take it at E, right, if we take the moments at E, it's going to allow us to solve for AY, right? And the unknown for EY is going to be eliminated from that equation. So let's take it from E and solve for AY, right? So AY multiplied by the distance. And then we're doing the point loads here. And then also the distributed load, right? So this distributed load, we can get the magnitude of this distributed load by multiplying it by how long it runs over, right? So 48, it runs over 9 meters. And then we also want the lever arm, right? The lever arm of this point load will be in the middle. So it's basically here, right? So 4.5, right? This gives us AY, it's this, kilonewtons, right? This ring a bell? Okay, and then we can either take the sum of the moments again at A this time to get EY, but of course that's more annoying than taking the sum of the forces. Because we only have one unknown force now, we can use some of the forces in the Y direction. AY plus EY minus 27 minus 27 minus 48 times 9 meters, right? Because it acts over 9 meters. This gives us that EY is 243. So I actually didn't need to do that calc if I didn't want to, but it's basically because we have uniform loading on the beam, because we have symmetrical loading on the beams would be taking the same amount, right? So if you wanted to be quicker in the exam, you can just do all the downwards forces divided by 2. So that's how much each support is taking. Right. That you can only do that in the special case that it's symmetrical, all the loading, and the shape of the beam as well. Okay. Okay. So we basically know that this is 243. We know that this is 243. Right. So let's draw the shear force diagram. So this goes up by 243. Right. And it's going to taper down by 48 kilonewtons per meter. And if that's over 2 meters, that gives us 147, right? And then it's going to drop by this point load, right? So a 147 minus 27 gives us 120. And then it's going to keep tapering down. We know it's going to be symmetrical, right? So I can actually just speed it up. Looks like this, right? So actually what I'm going to do, so this is all your positive shear, this is all your negative shear, right? Sorry, I'm going to add some pages. So what I'm going to do in order to get the bending moment diagram is split this shape up. I'm going to split it into just rectangles and triangles, right? So I'm going to find the area of these shapes, and this is going to help us integrate it. This is basically just a shortcut. So this will help us find the bending moments at these points. So basically, that first shape is going to be a triangle, so it's base times height of the triangle. The base is 2 meters, right? And the height is going to be the difference between 243 and 147. Right, let's calculate that later. The second shape is going to be the area of a rectangle. The area of a rectangle is going to be 2 meters again, multiplied by 147, right? And that third shape is also going to be a triangle. It's going to be, basically here is going to be 2.5 meters. Right. So half 2.5 multiplied by 120. Right, let's see those values. 96 kilonewton meters, 294 kilonewton meters, 150 kilonewton meters, right? All good? So how's this going to look on a bending moment diagram? It's going to be like this. Do I draw it? Which way do I draw this? Okay. Draw it the legit way. It's going to be two kind of parabolas like this. Okay. Basically, as we walk along the beam or consider more and more of the shear force along the beam, we're trying to find the area underneath here, and that will give us this point for the bending moments, right? So this is going to be the first and the second shape added together, which gives us 390. And then in order to get that shape, that's going to be 1 plus 2 plus 3 as well, because now we're going to be considering all these shapes here. It's going to give us 540, right? Okay. Is anyone lost here? So we're basically just finding the bending moment of a simply supported beam, but it looks slightly different to your normal case because we also have point loads acting on it, right? So those point loads acting on it, as well as that uniformly distributed load, will make it look like this. Okay. Cool. All right, so basically this was just an effort to find M star. M star will be our critical section, which will be in the middle of the beam. And it's going to give us the highest bending moment. So when you have highest bending moment, that's the point which your beam is most likely to fail, right? So this, in our case, will be the middle of the beam. This tends to be the case for simply supported cases, unless we have like uneven loading or something like that, right? I can see a couple of people copying this down. Do you guys need more time for this? I'll upload this as well to my notes folder, so you can have a look at it as well afterwards. Okay, so once we're done with finding the external loads, now we have to work towards finding the ultimate moment capacity, right? So this is the strength of the beam. This is always done in pretty much the same way, right? The first thing we need to do is find the depth to the neutral axis. Okay, how are we going to do this? Well, we have to find the forces. And then we're going to take the force equilibrium. Okay, so to find the compressive concrete force, right, we have to find gamma and alpha 2. Gamma is this one. Alpha 2 is this one. No, my bad. This is 2.5. FC, right? We're given in the question that FC is 38 MPa, right? So that's actually on the higher side. So you won't see this number very often, but if you do a lot of these flexure questions, you're going to start seeing common numbers pop up for gamma and alpha 2. You know, for when you have like 32 MPa, 25 MPa, these numbers are quite common. So you also have to keep in mind these numbers have to be greater than 0.67, right? So this is like a hard cap for how low these reduction factors can get. So if you like super high strength concrete for 50 MPa, 60 MPa, you might start reaching these numbers. Okay, so this is going to help us find the compressive strength of the concrete, right? So let me just quickly draw you a visual. So what we're doing right now is we're trying to find, sorry, that's the stress. And this is the force, right? We're trying to find this big resultant force, okay? And we're using a technique called the rectangular stress block technique, where we have to multiply, why not draw it like that? I guess I will. If that's where the neutral axis is, right? The compressive concrete, the rectangular stress block has a depth of gamma dn. So gamma is a reduction factor, which decreases, so it's basically just shifting where that block is relative to the neutral axis up a little bit, right? This axis here is alpha 2 FC, right? So alpha 2 is also a reduction factor, right? It's reducing how much strength we say the concrete has. And this dimension here is the width of the concrete, okay? It's this here. So because we need the area of concrete in compression, we need to multiply it by that width as well, okay? If you're curious where rectangular stress block comes from, it's basically because engineers don't like to deal with parabolas and like Cook shapes like that. So we turn it into a rectangle because the other option would be doing something like that. This is like a parabola, and we've simplified the parabola. We've basically pretended it's a rectangle, shifted it up, reduced the maximum of the parabola's peak. Yeah. So this is actually the easy version. So yeah. And this is unique. Oh, it's not unique to the Australian standards, but Australians love rectangular stress block, right? Okay, so basically let's find all those multiplied together. So it's gamma dn on this axis, right? Alpha 2 FC on this axis, and the width, right? So now we've got the force. We've got what this is equal to, because we multiplied the stress, right, by the area of concrete in compression. Right. By the way, the stress was this part. Right. So this is the stress magnitude. It's like for a beam when you have a distributed load, it's like that magnitude of how much stress is acting on it, right? Whereas this gamma dn is this dimension of the concrete which is in compression, and then b is just the actual width of the concrete. Okay, but we don't know dn basically, right? So we can solve all this stuff in terms of what we know, like this, and 38, right? We know the width of the beam, which was 350, but we don't know what dn is, right? But this is all going to play into when we solve it using a force equilibrium, right? It just gives us some constant and then dn. Okay. Now we can take the force to equilibrium. So there's only one other force acting here because we only have to consider the tensile steel, right? So in terms of the stress in the tensile steel, this comes with an understanding of whether your tensile steel, compressive steel has yielded or not. And okay, maybe I should talk about what determines yielding. Remember when I was talking about strain, right? So when you pull the concrete enough, when you pull the bars enough, or if you push the bars together enough, they reach the yield point. They reach when the bucket is full, right? That's when your stress is equal to FSY. That amount that it's stretched is dependent on how far it is from the neutral axis. So the further away it is from the neutral axis, right, the more likely it is to be yielded, right? So when we're designing doubly reinforced concrete, we generally consider the tensile bars as yielded, and the compressive bars as not yielded, because the compressive bars aren't pulled very much. Oftentimes, the compressive bars' only role is to shift the neutral axis up, right? It's to shift the neutral axis up so that the tensile bars can do more and take on more force, basically, right? Does that make sense? Yeah. You always put more tensile bar in concrete than compressive bar for this reason. You add in more compressive bar, you're just wasting money. It's not going to do very much in terms of actually adding capacity to the concrete. Okay. So let's just consider the tensile bar yielded because that's the normal case, right? All right. So in that case, it means that our formula will be really easy for force equilibrium. So we're going to take the compressive forces are equal to the tensile forces, right? Which just means this shit. Is equal to FSY AST. So FSY AST is stress multiplied by area. What does that give us? Force. And specifically, that's the force of the concrete. Of the steel. But it's only the case when your bars are fully yielded. When your bars aren't fully yielded, like if we have compressive bars, this formula will be a little bit harder to fully express, right? But since we've yielded, FSY is like that, and AST, let me check the question again. It should be above given in the question. The area is 3720 millimeters squared, right? So solving for dn is quite straightforward when we don't have compressive bars. Compressive bars usually aren't yielded, and it will result in a quadratic equation for dn. Right, it's going to be dependent quadratically. But here, this is a simple matter of dividing the right-hand side by the left-hand side's constant in order to find dn. So when you just have singly reinforced concrete, it's quite simple to solve, right? This gives dn is 201.55 mil. Okay, great. Now we have to check the steel, okay? Okay, basically, you have to have an understanding of what we're checking. So when I say check steel, it's not like the tradie site term, like, oh yeah, steel's there, we've counted it up correctly. It's whether your assumptions are right or wrong. You hope that they're right so that you can continue. What assumptions are we assuming? So for singly reinforced concrete, we just assume the steel was yielded right. If we check it and it's not, it means our assumption was wrong, you have to redo it, right? So if you've assumed that your tensile bars haven't yielded, but they actually have, you gotta redo it. That's why I'm telling you, if you have tensile steel, it's usually yielded, okay? Okay, so how do we do that? Let's draw out it probably helps to draw out the strain diagram. All right, this point is what number? It's always 0.003, right? This is dn. Perfect. dn was 201.55, right? And we have our steel here. So this is going to be epsilon st. So how much our steel has strained, okay? We're given in the question, this depth is 485, right? Just gonna move that to the side. Okay, so oh wait, Farhan's gone, never mind. Okay, basically here's what it looks like. If you were looking for a formula, you can do it kind of like this. So this is the depth to neutral axis. If you wanted to skip a step, you can do it like this basically. So I got this from similar triangles, but what I've, literally all I've done is rearranged the similar triangles, right? So we had the rise over run, right, of that small triangle. Wait, let me just highlight it. We had the rise over run of this small triangle, and we know it's equal to the rise over run of this triangle, right? And so we've literally just rearranged it to solve for the rise of the orange triangle. That's literally all we've done. So 0.0042, okay? And we have to check that it's yielded, so it has to be above some threshold. That threshold is 0.0025. Why is that? We call that epsilon sy. This is the steel yield limit. This is basically how big your bucket is, right? This is basically the strength of the steel divided by the elastic modulus of the steel, right? So in our case, we had 500 MPa steel and 200,000 MPa modulus, right? That's where that comes from, 0.0025. That's a number you can memorize to make it faster in your exam, but it will change if either one of these things changes. This number will change if you have a slightly different steel strength. It will also change if you have a slightly different modulus, right? Okay, but since we have this left number being bigger than the right number, that means our assumption was correct. That means we don't have to go back and redo everything. So it's all good. But you have to do this because if you don't, you lose marks basically. If you just assume that your assumption was right. Okay, so now we've found dn, we've checked the steel has yielded, and now we have to find the moment equilibrium. We have to find the ultimate moment, right? So here's where the shortcut comes in, right? Sorry, one sec. That is, oh yeah. Okay, so we're going to take the sum of the forces about the neutral axis, okay? And basically it's gonna be the spin due to both these forces, okay? Now, thing is, when you have singly reinforced concrete, aka no compressive bars, there's a fast way to do this and a slow way to do this, okay? So in order to tell you how to do it the fast way, right? Which force do you reckon is easier to calculate, CC or TS? TS is much easier to calculate. And we can use something called the force couple method. We know that the forces going left is equal to the forces going right, because it's in equilibrium, right? We don't need to calculate what CC is, because it's going to take longer. It's a longer formula. We can simply take that force of TS and take the lever arm of it. Okay? basically it's saying instead of taking the sum of the forces at the neutral axis, if we take the sum of the forces here, right? Remember these are our lines of action. If we take the sum of the forces there, we can ignore CC. So we simply take this number and multiply by this lever arm instead. This is actually where flexural design steps come from. So as you're looking through the flexural design steps when you're studying, this is how they can find out the forces of the concrete without necessarily how much steel will be in the concrete. They can take the sum of the forces here and ignore how much AST we need. Right. So this is a very common method that they utilize. Okay, so let's do that. So we're gonna take TS, right, which is AST FS, right? And we just need this lever arm, right? Thing is, what do you guys reckon this distance is from the top here? Remember, this is due to the compressive concrete block. This was that when we were just talking about the stress. So what do you reckon that is from the top? Yeah, very good. So, because this was gamma dn, right? When it was a stress block. This is now gamma dn on 2. Got it? So what we have to do is we have to take 485 and subtract gamma dn on 2. Right, so what we've done is we've taken this, subtracted this, and it gives us this, right? dn was this number here. Gamma was 0.875. So this is the fast way to do it when you have singly reinforced concrete, right? We know how much steel's there. Go 3, 7, 20. This is 500. So this will give us a number that looks like something like that, right? Because everything we've done is in newtons and millimeters and MPa, right? Everything we've done is going to be MPa, newtons, millimeters, right? However, when we're expressing our final answer, it's good to convert this to kilonewton meters, right? Which is you divide it by 10 to the 6. Right. And then you get kilonewton meters. Does that make sense? So that's our answer for mu. However, what they care about is phi mu. Okay, so phi is your capacity reduction factor. It's saying that we don't want to think that our concrete is as strong as it is on paper because there's a chance it will fail, right, earlier. Sorry, this is really getting into... Sorry, I'm getting nerdy about this because this is what my thesis is about. But basically, this number can vary it can vary between 0.65 and 0.85, depending on ductility, right? So in the best case scenario, it's very ductile, it's 0.85. In the worst case scenario, it's brittle, so it can fail more easily, it's 0.65, okay? So how do we calculate what this number will be? We have to calculate something called the ductility constant. The ductility constant is represented by Ku, right? And it's a ratio of, so if let's draw the strain diagram, why not? So this is the depth of the neutral axis, right? dO is the depth to the outermost steel, okay? So if you have two steel layers, right, the furthest away from the compressive fiber is what we take as the depth, as dO. Okay, so this ratio has to be basically the lower the better, right? So if it's beneath 0.36, it basically means that it's fully ductile, right? Which means that your capacity reduction factor is 0.85, right? But if it's above 0.36, we have to linearly interpolate it, which I'll show you how to do in a second. But one thing you can do to improve the ductility is add in compressive bars. Why is that? Well, it's because if you add in the compressive bars, it's going to shift the neutral axis up, causing this to, causing dn to be smaller, causing ku to be smaller. Okay, so there's a lot of nuance to this kind of, I don't know, this like seemingly simple calculations. I don't think each of these individual steps are too bad, but just trying to find the way to like put them all together is kind of the complicated thing for students, right? All right, so this was 201.55, right? The depth to the outer steel was 485. This gives us a ductility of 0.4156, right? Which of course isn't less than 0.36, right? So we have to do this linear interpolation. So basically this number, in the case of linear interpolation, is 1.24 minus 13 over 12 times that ductility constant. So that was 0.4156, right? Giving us a capacity reduction factor of 0.7898, okay? This gives the answer to our question as phi mu is 0.7898 multiplied by this number here. Okay. There's actually more to this question, believe it or not. We haven't even finished one question, by the way. So basically the last part of the question is saying, okay, well now if this doesn't satisfy the ductility range, which it doesn't, right, because this is greater than 0.36, add compressive steel until Ku is 0.3, right? So we can basically backwork this, right? And find that we're looking for a dn of this. So this was 485. We're looking for a depth to the neutral axis of 145.5 in order to satisfy this range. Right? Okay. So now we go back to the force equilibrium because we already know what dn has to be, because it has to satisfy a ductility range or ductility constant, I guess, right? So we use our force equilibrium. We have all the compressive forces is equal to all the tensile forces, right? So we call compressive concrete CC, compressive steel CS, and tensile steel TS, right? This doesn't change, right? This will change based on dn, right? So this is alpha 2, FC, gamma dn, B, right? Oh, I can't read my writing. We know what dn is, right? 145.5. We know what the width was, 350. Okay, here's the cooked part. So CS, right? We've established it's the area of the steel, which we're going to have to solve for, right? But are we going to assume the steel is yielded? No. Because compressive steel, right, it sits too close to this triangle to be yielded, basically. The further away it is from the neutral axis, the more likely it is to yield, right? So we're going to assume it's not yielded, right? This then becomes the strain of the steel multiplied by the, that's the modulus of the steel multiplied by the strain of the steel. What's this? Use similar triangles, right? Oh, sorry, I had to draw it out. I didn't write down my working for this. fuck. 65 from the top is where the steel is positioned. DN is 145.5, right? Okay, rise over run is equal to, the rise is this, right? Over run is 145.5 minus 65. Okay, so we rearrange for this, we get 0.003, 145.5 minus 65 over 145.5. Okay. We know this is 200,000 MPa, right? And now it's just a matter of multiplying this all together in your calculator. You're going to find that sigma CS is 331.96 MPa. Okay, and we solve for this. We get the area of steel you got to add in 1558.163 millimeters squared, right? Okay, so basically this is like a decimal. You're basically never gonna find the bars, because the bars come in standard sizes, right? You're never gonna find bars which match this exact amount of area, right? So what it's trying to say is we need the KU to be less than or equal to 3, right? So so basically we need to find steel bars, right, using our table of the nominal bar areas, which is going to be greater than this amount, right? Because you have more compressive steel, it's going to shift the neutral axis up more, it's going to make it more ductile, right? So if we use 4 N28 bars, it's going to give us 1,800 millimeters squared, right? So that much compressive steel area, right? Last, we have to check for our steel yield. Okay, so check steel yield. That's literally just a matter of copying this line. And this should be less than this amount, basically, because it hasn't yielded yet, right? So basically, if you want to go overkill in this question, I'm assuming if you do this, you'll already get full marks. But if you want to go overkill, this will give you a new DN, which is less than 145.5. So this number is actually not accurate. It'll be like 138 or some crap like that, right? For example. And then you can solve it. But if this satisfies it, all right, then the previous, then the depth of the neutral axis, which is less than this, should satisfy it, basically, right? Okay, so that was one question done. What I'm gonna do is I'll give you guys a break. Go get some refreshments, go to the bathroom, all that. We'll come back and we'll choose another question to do. I'll show you the questions again. Come up the front as well if you have any questions for me. Yeah, right. All good. This one?
Yeah, sweet, thanks.
All good.
We're just finding the middle energy. Yeah, I think that's the minimum compressive area we need.
For this last bit, for the force equilibrium bit,
Yeah.
are we finding for ASC?
Yeah. It's asking for how much compressive bar area would you add in.
Oh, at the top. Oh,
Yeah.
okay. And you're finding this because the K value was bigger than 0.3?
Yeah. So the K value was like 0.41.
0.41 something.
And then it was like, okay, but now we want to add in enough compressive bar to shift the neutral axis enough up
Yeah.
and make that K value lower,
Oh.
which will make it 0.3. KU of 0.3.
Oh, that's fine.
See, man?
Oh,
That
okay.
is-
Is 0.3 from the standard, like A3600 standard?
No, that's a designer recommendation.
Oh, okay.
Oh.
So it will say it in the exam.
Okay.
It'll be like, we want it to 0.3, or sometimes it'll say 0.25.
Okay.
So yeah, there's no formula for it because yeah, so many things just depend. You know what
This
I mean?
is like the top. The spot is for so they're adding a
Hey man, what's up?
Just want to ask about the flexure stuff, right?
Yeah.
Assuming that, for example, like for the uniform load, the 1.35G is the governing one, but for the point load, it's like assuming it's a life load, right? So it's like because I'm 1.2 and 1.35. What do we choose then?
Wait. Oh.
Wait.
Oh, you mean like a point dead load?
For example, like a simply supported beam.
Yeah, that's right.
Yeah, then in the uniform load, similarly like there's only like dead load, and there's like a one like life load, like P, for example.
Okay.
So what we calculate, for example, in uniform this was governed, and for the point load, this was governed, right?
So you can never mix and match. So what you need to do, or ultimately what we're trying to find, so this is PQ, right?
Yep.
And you're saying all of these are
Uniformly dead load.
WG, right? So how do I unlock that one? Okay. Basically, case 1 is only dead loads. Right, so this case, you just look at the uniformly distributed load. You ignore the point load completely. Case 2, 1.2G plus 1.5Q. Right. So you still need to factor in this because that's a dead load. But now here's where you factor in that live load as well.
No, that's concrete. No, but like, this goes through some.
Does that make sense? So these are the two beams you're analyzing.
Yeah.
They have, oh sorry, it's the same beam, but they have two different load cases, and whichever one's going to give you the highest M star is going to be the one that governs, right?
So it's the one, the M star dead matter. Yeah, thank you.
So you never mix and match.
I'll just go for one way.
Sometimes it's hard to tell, but usually it's quite easy to tell. Usually it's live and dead.
Yeah.
The only time, I'll give you an example, right?
If it's live and dead, like 1.2 thing will like govern like majority of the time.
Yeah, because I'll tell you exactly when it doesn't govern, right?
Yeah.
No, but I think if you have some supervisor, you're gonna cover this. But I think we'll nitpick.
Let's say WG is 30.
Yep.
Right. And let's say these live loading, the load patterns are both uniform, right? What value of live load does it need to be in order to split the threshold, you know what I mean? So 1.35G 1.2G, and 1.5Q. Right. So what value does it cause? It causes this top one to govern for live load. Do you know what I mean?
No.
Oh, sorry. Okay. So basically, if this number's really high,
Yeah.
which one's going to govern?
The 1.2.
Exactly. What if this is a little lower?
Then the G can govern. The 1.3 can govern.
But in this particular case, it's actually still this one.
Yeah.
What number does this need to be in order for this one to govern?
Or it should be equal to 1.3 G. Then you can find the Q.
Yeah.
Yeah.
But actually, what it is 1/10
110.
is the threshold number.
Oh.
So this literally needs to be 2 in order for this one to govern.
Which is very
That's very unlikely, yeah. But that's the rule of thumb.
dumb. Okay. Thank you.
All good. Yeah.
Are you doing research thesis?
Yeah.
What's the WAM cutoff? 70, right?
I think so, yeah.
70.
Oh. What's the other one?
You don't get the It's crazy.
I wanna say this next one.
So it'll say honors mode, but it won't tell you guys. But also you don't have
All right.
Yeah.
All right. You guys ready? All right. So we're gonna do the next vote for the questions. So we've done flexure. Put your hand up if you want to do shear. Okay, chuck your hand down. Put your hand up if you want to do serviceability. Put your hands down. Okay, what about, put your hand up if you want to do columns. Put your hand down. What if I told you we can do a column? It's gonna take a while, but it's gonna use almost the exact same techniques you learned. I mean, there will be more stuff as we just learned. Is that gonna change your decision? Wait, chuck your hand up if you want to do shear. Chuck your hand down. Chuck your hand up if you want to do serviceability. Chuck your hand down. Chuck your hand up if you want to still do columns. Chuck your hand down. Chuck your hand up if you want to die. Okay. All right. Let's do shear. Okay. Should we do the shear force envelope or the one with slab? Envelope? Okay. 2021, question 5. Here's the question, just give it a read. I'm going to get my notes up. Okay. So, okay, basically here's how it works. So you're gonna have to apply what we did before, right, to find shear, and then we used it to find M star, but I'm pretty sure we don't need M star, right, because we're gonna use the simplified method. When you have the simplified method for shear, where does it say it? Yeah, simplified method. Once you use the simplified method, you don't need to find the moments, because the detailed methods will require the moments as well. Okay, so we're gonna need to do it for 3 different loading patterns, basically, and then create an envelope called the shear force envelope, which takes the worst case scenario at the supports of your beam and the middle, I think, the middles of the beams. Yep. Okay, so let's quickly read the question. So we have unfactored dead and live loads again. And then we have this cross section, right? And then draw shear force diagrams for only case A and B, right? Case C is already given. So if you look at the next page, that's case C with that specific loading pattern and the shear force diagram already drawn for you. So you only need to do it twice, basically. Case A, the factored live load and dead load, the factored dead and live load act on the entire length of the beam, okay? Case B, the dead load acts on the entire beam, but the live load only acts between B and C. Okay, and then case 3, which they've already drawn for us, the dead load acts on the entire beam, but the live load act between A and B and between C and B. So basically, this is dead load, right? For the case they've already drawn for us, that's where our live load sits, right? Okay, case A, was live loads spans across the entire beam. And then case B is the live load sits between B to C. Are we all on the same page? No? Okay, basically, we just have 3 different loading patterns. We know what the dead loads are, we know what the live loads are. The dead loads are due to things in the beam which don't move, right? Like the soft weight. If we were calculating, I don't know, if this was quite heavy in the civil building and it doesn't move, this would be a dead load because it's something which is fixed in place, right? Live loads are things which move around, like humans, like traffic, in the case of like bridges, for example. It's things that can vary. So we're varying where the live load could be positioned, okay? So when you have live load acting on an entire beam, right, what happens is generally it causes more loading on the support, okay? What happens when you have live loading only acting on certain parts of the beam, such as between A to B and between C to D, like they've drawn in case C here, is that it actually tends to exaggerate the shear force in the middle of the beam. This will be made more apparent in a second. Right, here's another case. So if the live load's just only on this part of the beam, it's going to exaggerate the shear force in certain parts of the beam, basically. Okay, why is this important? Okay, well, you'll see when we do it, right? So like, let's do case A. It's going to look like this, right? We're going to use the factor for dead load and live load, like this. I think I just swapped the colors, but ignore that. Okay, all these numbers, 30 and 22. Let's calculate what these distributed loads are first. Whatever now. Let's see. Sorry, my arithmetic's really bad. Okay, that's that. 1.5 times 22 is 33. Okay. So why are we not considering this loading case? You'll almost never govern, that's why. Because I was saying to a student who came up in the break, the only case, okay, let's pretend this is a beam that has live load and dead loading on it. So that's your, I guess let's say dead load, this is your live load, right? So if this is, for example, 30, right? WG is 30. This is unfactored load. So this isn't the question that we're doing right now. but this is just to give you an example, right? What value of live load do we need for the case of just dead load alone to govern? If this was 50, would dead load and live load govern, or just dead load? Let me put it like this. This is just the dead load case. This is the dead and live load case. Which one would govern if this was 50? The top one or the bottom one? Bottom, right? What if it was even? Bottom still, right? What if this was 10? Hard to tell, right? Well, it turns out the threshold number is this dead load has to be 1/10. Sorry, the live load has to be 1/10 of the dead load in order for it to be even, for both the loads to give the exact same number for the case of the beam, being like distributed over the entire, load, right? If this was less, then this case governs. Do you know what I mean? It's like a negligible live load. Sorry, I'm really nerding into this because this is what my thesis is also about. I think I drew the beam wrong. Sorry, because the support was here, right? So this is 2.5 meters, 2.5 meters, 2 meters, okay? And B is that point in the middle of the beam. So that's what our beam looks like, okay? All right. So let's draw the shear force diagram. Oh, let's find the supports first, right? So let's call that AY. Let's call that CY, okay? Which one did I do? I got AY, so I did this one. So AY, right? It goes this way, right? So that's going to cause a clockwise moment. And then this is going to be 5 meters away. So we're looking at this lever arm, right? Okay, and then next we have these, the middle of these loads, right? Situated 1.5 meters away. So basically, here's 2 meters, right? This is 1.5 meters because it's in the middle of the beam, right? Whole beam is 7 meters, right? So yeah, use a bit of geometry there. This causes a clockwise spin. Sorry. 36 plus 33, because these loads are currently overlapping in the same spot, right? And it's 1.5 meters away. We solve that for AY, and we get AY is 144.9 kilonewtons, okay? We're going to take the sum of the vertical forces, which gives AY plus CY minus these two numbers, right? 36 and 33. Gives us CY. It's 338.1 kilonewtons. Oops. And that's these two numbers. So you can do a sanity check, because if you have unevenly spread out supports, right? So before we had the case of the supports being on both ends, right? And it was symmetrical loading that took on the same amount of force, right? Which support do you think is going to take on more forces? Which one's going to react more? It's going to be CY. So basically, imagine this much of the beam is being loaded on CY, but only this much of the beam is being loaded on AY. Do you know what I mean? So like the majority of the beam is being carried by CY. Right? So like it makes sense that these numbers are about these magnitudes, right? Okay, cool. So now we're going to draw the shear force diagram. We're not going to draw the bending moment diagram because it's not required for the question. So this goes up by AY. This goes up to 144.9, and it's going to sink by this rate, right? I should probably express that these two together. 69, nice. And then it's gonna fall at a constant slope, right? Look like this. And then it's gonna shoot up by CY, and CY is bigger, right? And then we know that for a shear force diagram, the shear forces will start and end at 0, right? So this will be the rough shape that we're gonna use. And here is going to be negative 200.1, and here is going to be 138, right? So that's at position C. Oh, I guess both of these are at position C, right? This is position B, and this is position A. This is position D, right? So we know what A, D, and C are, right? But is a position, sorry, is point B going to have a shear force of 0? Remember, point B was 2.5 meters away from the left edge. You can't exactly tell, right? You can't assume it's 0. How would you find this? Well, you can use linear algebra, right? So the shear force at B, for example, will be this number, right? Minus this slope, right? What's this slope? 69 kilometers per meter. Right? This gives us negative 27.6. That's actually what so it's actually here. So this is the position of B roughly there, right? Or I've drawn the magnitude slightly wrong. So this one should be bigger, like that. Or whatever, you get the idea. Okay, all good? So that's case A done. Don't do case B. Just gets more and more fun. All right, so case B, let's copy this over. We can't consider the live and dead loads together anymore, so we can't use 6.9 because they're not like loaded in the same way. They're loaded like this, right? So that part is going to have 33 kilonewton per meter, whereas the rest is going to have 36, right? And then in this middle part, they're going to be overlapped, right? So let's do that again. Let's take the sum of the moments, right? Sorry, one sec. Fuck, let's go over. Take the sum of the moments at C, again, find that it's going to be negative A, this is going to be the same, so it's 5 meters away, but now we have, let's do the dead load first. The dead load is not going to change, it's just going to be 36, and it's going to be 1.5 meters away, right? But now, so this is 2 meters away, right? The middle of this load is going to be slightly differently positioned, right? How am I going to say this? Basically, this whole thing is 2.5 meters, so half of this is going to be 1.25 meters, right? So it's going to be 33, 1.25 meters, right? Have I done something wrong? I feel like I've done something wrong. Okay, so basically I forgot to multiply these distributed loads by... So I've just done lever arm and distributed load, but we have to multiply it by how much length the distributed load acts over, right? So let's do that again. So instead of just 36, we're also gonna have this, which is 7 meters, right? And instead of just 33, sorry, this is going to act over 2.5, right? So now it's correct, sorry. So now we solve for AY, and we get AY is 96.225, and CY, sorry, the sum of the moments, sum of the forces. AY plus CY minus 36 times 7 minus 33 times 2.5, right? This gives us Cy as 238.275 kilonewtons, okay? So now we've finally solved the support reactions. I'll keep that there, but I'll make it a bit smaller. Right? Let's draw the shear force diagram. Oops. It's like this, right? So similar shape, but it's going to be a bit different, okay? Do it with a good pen. So AY was less this time, right? AY was only 96.225, right? And then it's gonna have one slope, right? And then it's gonna increase its slope. So why is it increasing its slope? It's because it's stacking on live loads, right? So this middle part of the beam is gonna have the greatest slope, right? So it's gonna have this very gentle slope, and then it's gonna cross over, be more shallow, rise up by Cy, and then follow the shallow slope again, right? Let's calculate these points. So if you're confused where that came from, let's run through it. So this slope was simply the dead load, okay? So it was 36 kilonewtons per meter. That's the slope. This slope was our 69 kilonewtons per meter, and then this slope was our 36 kilonewtons per meter, right? So we just have two different types of slopes happening throughout the whole beam, right? So this amount turned out to be 6.225. This amount here, negative 166.275. Let's do this point first. This one, 72, and of course this is 0, right? Got it? So this was our second case. Luckily they don't make us drill a third case because I know how tedious this whole situation is, right? But yeah. Okay, how do we draw an actual shear force envelope now? Because all we've done is bloody do 1300, right? So how we draw a shear force envelope? Is we take the worst case scenario from all three. So let's have a look at it again, right? So this was case, what did I say A? This is B. This is case B, right? This is what our shear force looked like in case B. This is what our shear force looked like in case A. And here's what our shear force looks like in case C, right? So the notable things are in this case, right, where we have the live and dead loads acting over the entire beam, we have the highest shear forces at the supports, right? Well, it's matched here, but we have 200 is greater than 138, 145 is greater than 124, right? However, when you have just the shear forces acting over the entire, when you have both the live and dead loads acting over the entire beam, it's going to under-exaggerate what the shear forces are in the middle of the beam, right? It's going to say, okay, there's 0 shear force in the middle of the beam. We know that's not necessarily true, right? So that's why we need to account for case C, which gives a shear force of negative 48.2, and case B, which gives a shear force of 6.225, okay? Here's how it's going to look. So basically this value is going to be from case A, it's going to be the high one. Then it's going to go over until the highest case at point B, drop to the lowest case at point B, and then go back to the lowest point, the highest magnitude at the support. And highest magnitude at this support is going to look like this. That's 138, that was 145, you know. That was, what was it, 6.225, I think it was. This was negative 48.2. This is negative 200.1. So negative 200. So let's just analyze that. That's from case A. That's from case A, and I think also maybe it was C, I think. Yep. This was from case B, and this was from case C. This is from case A as well. So again, case A governs the shear force of the supports. Case B and C are purely for those the shear forces in the middle of the beams, not at the supports, right? Okay, that's not, yeah, we haven't gotten that far in this question yet. Okay, so what we need to do is we have to calculate the critical shear force. What's the critical shear force? It's the shear force right here. So it's this distance away from the support D, okay, where D is the same as this. So if we have cross section that looks like this, right, and a steel looks like this, right, D is the depth from the compressive face until the middle of the tensile layers. So this is called the effective depth, right? So what happens if we have 2 layers of compressive steel? Would it be at the outer layer, middle, inner layer? So if we have 2 layers, D changes to be in the middle because it's in the centroid of the tensile bars. That's where it's measured until. But if we only have 1 layer, it's just the middle of the tensile bars. Okay? So that's D. So that's how far away we need to be from the support, okay? In our case, that distance was 450 mil, okay? All right, so now we have to calculate the critical shear force. So we can do that whole linear graphing method, right? So you start at 145, right? And then you subtract the slope, right? So what's the slope? Well, we actually have to find it, but it's like rise over run, right? So rise, I already have a subtract here, so over, goes over 2.5 meters, I believe. And we have to multiply it by that distance, right? This distance, right, are we gonna chuck in 450? What happens if we chuck in 450? If we chuck in 450, it's gonna represent this line because we're working in the wrong units. So this is gonna be 0.45 meters, right? So don't fall for that mistake, please. Okay. I wrote the wrong number, sorry. That's 449. That's 4. Yeah, no, jokes. Same thing. That gives 119.9 kilonewtons, okay? So this will be our critical shear force, which we have to check for. This is the point at which cracks and stuff tend to form on the beam, right? So if this was like 2D shape, this is the point where our, let's go that way. Does it go up or does it go down? I forgot. Anyway, that's where your shear cracks will start to form. Okay, now we've done the left-hand side. Kind of do the right-hand side. Okay, so step 1. We have to check that V star is less than phi VU max. Okay, this VU for shear is always 0.75. We don't need to do any ductility checks or anything like that. The capacity reduction factor is always the same. Okay, so VU max is basically a web crushing failure. So it's basically saying in the case of concrete, which looks like an I-beam, our web is likely to fail before everything else in shear, right? But usually this doesn't govern for a rectangular section, but we still have to check it anyway. It's part of the standards, right? The thing is, VU max is kind of annoying to calculate but it's gonna make us calculate values which we're gonna need for the remainder of the calcs anyway. So this is the formula for Vmax. So when I say that shear and serviceability are kind of topics that you can just use formulas and memorize, I'm not kidding. This is just going to be a bunch of following formulas. This is theta V, theta subscript V. We're going to use the simplified method. In the exam, you're going to expect the simplified method for shear, right? So there's a few simplified methods in the standards. This one's the simplified method for shear design, I guess you can say, where we take theta V is 36 degrees. We don't need to do any calculations further than that. And this will also result in kV is equal to 0.15, I believe. Yep. Okay, cool. So what I might do is I'll move this down. Okay, so FC is given in the question as 25 MPa. BV is the shear width, right? So, okay, basically, when you have an I-beam or a T-beam, that's more likely in this course, right? Which part do you reckon is going to fail first in shear? In terms of, this is the web width, right? Sorry, this is the flange width. Let's call it BF, is width of the flange. This is called the web width, right? Which part do you reckon is going to fail in shear first, or more likely? If you've done solid mechanics or steels, this might ring a bell. No. So, okay, basically, here's what the shear distribution will look like. You don't really need to know this, right? So this is the shear stresses, right? If we map it to the depth, we have way more shear stresses when the width is smaller, right? The smaller the width, the greater the shear stresses, right? So if any part's going to fail, it's going to be this part in shear, okay? It's going to be the area of less width, I guess you can say. So the shear width is always going to be the web width, or in our case, since we have a rectangle, it doesn't, what I just said doesn't matter. But like, if you have a T-beam, this will matter, right? So this shear width was 300 mil. DV, okay, DV is the internal lever arm of your section, which has this formula, right? So D, as we mentioned, is the effective depth, and this was 0.45, right? Sorry, let's do it in mil, my bad. 450. And the overall depth of the section was 500, okay? So the max of these two calculations, right, when you factor in these reduction factors, is 405 mil. So that's what value we're going to plug in for DV, okay? Okay, next, cot and this, right? So we said this was going to be 36 degrees. What is cot? Very good. So cot is the same as saying 1 over tan, right? So that's what we're going to plug into our calculator. Okay, what's cot squared? This whole thing squared. I guess you can just do this part squared. That's what that is, okay? Just keep that in mind when you're plugging it in the calculator. Okay. This is going to give, what's going to give this, right? It's going to give you an answer in newtons, right? Because again, we've been working in mil and MPa. So this is MPa, this is mil, etc. It's going to give you an answer in newtons, but we want to convert it to kilonewtons because kilonewtons are, I guess, nicer to present. So you divide it by 1,000 to get from kilonewtons, sorry, from newtons to kilonewtons, right? Okay, now we have to quickly check that V star, right, which was our critical shear at that section, is less than 0.75, which is our phi reduction factor, multiplied by this number. Just keep it like that. And it passes this check with flying colors. And again, this will only really fail if you have like a T or an I shape, not for a rectangle. This is a web crushing failure, right? Okay, so cool. Now we go to step 2. Thing is, actually no. Yeah, actually no, it's fine. Okay, so step 2, we have to check we have the minimum steel requirements. Oh, sorry, we just need to check what the minimum steel requirements are, okay? So this also has a formula. Okay. So fsy.f, right? That's actually given in the question. But I want you guys to have a think about this, right? Is fsy.f the same as fsy? So fsy is, what is it? The yield strength, yeah, of the steel, right? So fsy.f sometimes is a different number, but we only use it in shear design. So fsy.f is the yield strength of your steel when it's used as a fitment. Okay, so a fitment is one of these, also called ligatures, also called shear bars. So when doing shear design, you're going to run into fsy.f, right? I'll give you the rule of thumb. For N class bars, right, and for R class bars, our values are going to change a little bit, right? For N bars, usually both of these are 500 MPa. For R bars, usually this is 500 MPa and this is 250 MPa. But it will always be given in the question, but you have to be careful, these aren't the same thing. The yield strength of steel behaves differently in shear than it does in flexure and tension and compression, right? So if you remember, N bars are the ones which are ribbed, and then R bars are the ones which are not, they're smooth, right? So sometimes designers will prefer R bars because they're cheaper to manufacture, so they'll be more cost efficient. But sometimes, yeah, you need the better bonding, which will be, and your N bars, right? Those are your deformed bars with those like crisscrossing shapes on them. This will help it bond to the concrete better, basically, right? Anyway. Okay, cool, sorry, tangent. We were given that the concrete MPa was 25. We were, same thing, the shear width, and then fsy.f in our case was 250. Sorry, this isn't like a given. This wasn't part of the formula. I just wrote in these after this. So this was just a calculation based on these numbers. Okay, what's the next step? It's to calculate how much strength we have in the concrete in shear. Okay, so that's VUC, right? So this is the formula. This is 25. This we've actually already calculated. It's the one which is the max between two numbers. So when we do the web crushing check, it's actually already going to calculate a lot of these numbers, which we're going to see later on, right? So like you'll see KV, BV, and DV pop up. So once we do the web crushing check at the start, which is step 1, yeah, you just refer to these numbers again, basically. So this was 41.125 kilonewtons, okay? Okay, so given that our critical shear was this, right? Sorry, it was 93, right? What the hell have I done? Was it 93? Oh, sorry, I made a mistake earlier. What the fuck? What was it? 119.9. I think I screwed up the shear force envelope when I calculated the first time, and then I redid the shear force envelope and I didn't update these numbers. This should be 119.9, right? This has to be less than phi VU, okay? Now, it's basically saying, on the left-hand side, these are external forces, right? This is the shear happening on the beam at that critical point, right? And then here, it's the capacity of our reinforced concrete. However, what we're calculating at this stage is, can the beam withstand the shear without any shear bars, without the assistance of your ligatures, these ones. So we're actually calculating whether it's less than just the concrete strength by itself, okay? And the answer is no. And this tends to be the case unless we have slabs. Okay, so slabs are able to take on much more strength because the width of a slab is 1,000 mil, right? We do a strip for a slab. That's way wider. Once we have a really large width, the concrete can start taking on a lot more of that shear action. Okay, anyone got any questions so far? Excellent. Okay, that means you all understand 100% what's going on. Okay, so step 4. Now we have to add in stirrups, right? Stirrups, again, sorry, stirrups are just another way of saying these bars. The fitments, the ligatures, whatever. And we have to calculate how much spacing we need, okay? So here is the strength of the stirrups, right, in shear. Okay, so we're going to rearrange for that, and it has to be greater than this number. It might help if I write it like this, actually. Divide out the phi, right? So let's keep it in kilonewtons, right? Sorry, that's 119. Fucked it up by redoing my shear force envelope. Right? And this number is 102.075 kilonewtons. What it's saying is, okay, this is how much force the stirrups have to take in order for us to satisfy our condition, right? Okay, but the thing is, right, let's take a step back. Here's our beam. I'm going to do a 3D view of it, right? Here's the stirrups. And there's the axial bars and stuff, right? Thing is, what if we're looking at this cross section, which doesn't have a stirrup, right? So what if we're looking at this cross section here that doesn't have a stirrup, right? Then we don't have any shear strength, right? Like from the bars. What if we're looking at that exact section that our bars are on? Then we have all of a sudden quite a big jump in shear strength, right? So what determines essentially whether we account for the strength of the stirrup or not? Well, it's the spacing, right? We have to basically calculate how far apart these stirrups have to be in order to give us satisfactory strength over our entire beam, right? So if the stirrups are closer, if the spacing of the stirrups is closer, do you think that's going to be stronger or weaker? Yeah. So if it's further apart, it'll be weaker, right? It's closer together. You will have more over your entire beam, and it'll be stronger, right? So that's what we're going to do. We're going to calculate that stirrup spacing. That's literally as simple as this. ASV, which is the area of the stirrup, right, over S, which is the spacing, has to be greater than VUS, right, which is going to be this. We have to translate that back to newtons. over FSY.F, which is the strength of the stirrups in shear, right? DV, which is the internal lever arm, and cot this again. This is a simplified method, which is 36 degrees. This we've already calculated. That was the max of those two numbers. This one was given 250. Okay, so great. So now we have that the minimum area per spacing is this, right? And we just have to double check that this amount has to be greater than what we've calculated as the minimum area of stirrups per spacing. That was step 2. That was from step 2. So this was step 4, right? So this has to satisfy that, right? Okay, great. So the thing is, we don't know what the area of the stirrups are, and we don't know what the spacing is. We just know that we know what the ratio has to be. So what we have to do is we have to have a stab at what the spacing is, and then back calculate it later. So what we do is we start with a guess. 230 millimeters is a good starting point. The reason is, if you have your spacing too close together, it's going to result in this number being too low, right? It's going to be, I don't know, 500 millimeters squared. That would be an example of something which is quite low. So if you have a spacing of like 100 mil, it's basically, okay, we're going to pack the stirrups closer together, but the stirrups will be quite small. Like these might be like N8 bars. I don't know, like something really like ridiculously small. Okay. But basically 230 is like a nice balanced approach. You don't want this spacing to be greater than 300 mil, basically. So yeah, 230 is just like a good balance point, right? To calculate a reasonable area of steel. So with that guess, we can find the range of acceptable stirrup area, right? And now we can look at our table, okay? So the table which you're actually given at the back of your formula sheet, right? Oh, sorry, on your formula sheet, it's going to tell you the area of your, your N bars and stuff like that. So what we're going to do is we're going to choose one double-legged N10, right? So this means this has 2 legs, right? 1, 2, and these are N10 bars, okay? And the thing is, by the way, you know how I said this? Sometimes this is 250, sometimes this is 500 as well. These are just typical values for N bars and R bars, but always refer to what's written on your test. Because what it's saying is we have N bars, but they're 250 FSY.F. Oh, sorry, I wasn't done. And one single-legged N10, my bad. So that's a single-legged N10, right? Like that. This will give us the area of 3 N10s, right? Because basically how shear works is it cuts like laterally through this area. So shear area is actually the area of those bars, but it's kind of tricky. So it's not like the cross-section way. So cross-section way, this is obviously the area of your bars. This time it's like cutting through like this way, if that makes sense. Like that. Yeah. Okay. So just remember that spacing is 230 mil, we'll assume, and we'll just do all our design checks. ASV, when we consider this, right, it's 3 times the N10, is going to be 240 millimeters squared. And now we have to do all our design checks. There's a bunch. You ready? Okay, the first one's a max spacing check. This is big S dash. This has its own formula. If you want these formulas written out more nicely, I have notes in that Google Drive at the top of this document. And this document's just way better. I'm just scribbling at this stage. So basically big S is 500, and we have to check that our spacing that we chose, 230, is less than the minimum between 300 mil, half of our depth, and big S dash max. Okay. So that's 500, 300, and that was also 500, right? So the minimum number is going to be 250, right? So S has to be less than 250, and it was 230, so that's good, right? Okay, great. Our second check, let's call that check 1. Our second check is checking that the shear strength that we've determined is less than the web crushing failure. Okay. So we've actually calculated web crushing in step 1, if you recall. What we haven't done is we haven't recalculated what VU was. So we know what VUC was, but we don't know what the stirrup component's gonna contribute, right? So VUC plus, here's the formula for VUS, okay? So VUS is the area of the stirrups over the spacing multiplied by the shear strength of the steel when used as a fitment, multiplied by the internal lever arm, multiplied by cot theta V. This is 36. This was 405. This was 250. This was 240 on 230. This was 91.125 times 10 to the 3. We'll do everything in newtons, keep it dimensionally consistent. And then we're going to convert all of that. When we divide that by 1000, it will give us kilonewtons, right? So that is less than the web crushing failure is 794, right? And so that's okay. All right. That's our second check. Now our third check is checking that the area over the spacing, sorry, the stirrup area over the spacing has to be less than this, right? Which obviously, so that number was 240 over 230, which was 1.04. Has to be greater than what we calculated back in step 2. What was it? Yes, step 2. Right, and it is, so that's all good. Okay, last check here. Now we just have to check the final capacity, right? So this is 119, right, 0.9. Final capacity, which is the capacity due to the concrete and the steel, right, which we calculated as that, right? So this whole thing is equal to everything in here. When reduced by 0.75, has to still satisfy, which it does, and that's the end of our question. So yeah, there's basically 4 design checks: spacing check, web crushing check, minimum steel check, and the final capacity check. So once it passes all that, you've done the question. Okay, any questions? I'm sure you're all very drained. You know, feel free to pack up if you need to go. I also have a quiz if you like. If you want to test your knowledge, maybe this will be a confidence booster. Maybe you want to die after. Who knows? So feel free to join in on this if you like. I'm going to turn on the aircon. I'm like low-key on fire. Oh, sorry. Okay. That's the QR code. So I didn't plan this, but the questions you guys chose was flexure and shear. This quiz is mostly on flexure and shear, a little bit of material science at the start. It doesn't really have anything to do with columns and stuff or serviceability, I think, off the top of my head. For columns, yeah, I'll talk about that a bit more after the quiz maybe. All good. Good luck. Is anyone still joining? Is anyone still joining? Okay, good luck everyone. What the? Strange. Damn, the best idea. Maybe I'll give you another 30 seconds to a minute. Okay, there are 15 seconds left. Alright, 5 seconds. 5, 4, 3, 2, 1. Alright. Is everyone submitted? Alright, I'm ending it. Okay, congratulations. These 3 individuals. Okay, I'll just talk briefly about these things. 51% accuracy. Okay, so basically we have pure tensile strength and we have flexural tensile strength. These aren't the same thing. They're denoted by different letters. Yeah, so flexural tensile strength is where you have that strain curve, which is like 2 triangles. Yeah. And it's in flexure. Okay, so if a beam, this is serviceability related, right? But if the maximum moment on a beam is less than the cracking moment, the beam is not cracked. Makes sense. Okay. I cracked is the moment of inertia of the beam. And, IG is the moment of inertia of a beam before any forces have been applied to it. And I cracked is once it's reached the cracking stage. So once this has happened, basically, except this is greater than the cracking moment, then your beam is cracked. And as you can imagine, a lot of that concrete area becomes useless, right? Everything under the neutral axis becomes useless, and so it's smaller than IG. Let's see. The D-Owner's formula can be found by analyzing. So this is the cracking moment formula. The cracking moment is defined by basically the section before it cracks, right? And then what causes it to crack is, all these components, right? So you have to analyze the uncracked stage in order to find the cracking moment. So the depth of neutral axis in the uncracked stage, you use the transform section method and centroid formula. So we didn't talk about this today because it's only relevant to serviceability. My bad. In my head. Yeah, anyway, I forgot that we didn't cover this. But essentially, here's what it looks like, right? Here's what our uncracked section will look like. And we have 0 cracking, right? So we just use the centroid formula. Transform section, we turn the steel into concrete, and we can find DN. It's similar for the crack stage, except DN will be solved quadratically in the crack stage, because this DN, right, which is also it's the depth of the neutral axis, but it's also the height of the compressive concrete block, right? So there's actually 2 things depending on it, and so it's going to be solved quadratically. DN in the ultimate stage, this is mostly what we covered today. You do the force equilibrium of the compressive concrete and the tensile steel. This is for a singly reinforced beam, which only has your tension bars. Once we have compressive bars in there, this will actually become quadratic because the compressive bars haven't yielded. Right. This is a non-linear behavior now. Okay, N12 and R12 bars we mentioned are different. They have the same size, but they can differ in your stirrup yield strength. The shear force envelope, which is good, we talked about this today. This is like the case that we analyzed, basically. It's gonna be governed by case A at the supports, right? But in the middle, it's gonna be governed by the by case B and C, essentially. And here's what we've drawn. Okay, awesome. Right. Thank you very much for coming, everyone. Feedback forms are on the side. You're free to go.
Thank you.
All good. All good.